My name is Nejem Raheem. I am one of two economics professors here at Emerson College, and I welcome you to our event featuring Bill Scully and a bunch of other people who I will introduce. Before we get into the conventions of introduction, I'd just like to make sure everybody takes a couple of seconds to check that your devices are silenced and will not harass our speakers or panelists. Actually, just take a look. Because this thing sometimes, it turns itself back on. No, it's not right. Like that. Actually check it. It's good. You can do that. You good? Okay, good. Hi. Excellent. I'm so unused to lecterns, but I feel like I should be here. So, I'm going to introduce our speaker first, and I'll introduce our panelists. What do you think? Should I introduce the panelists at the end of the talk or now?
The end.
At the end, that's what I thought. That was my gut. All right. So I'm going to introduce our speaker, Bill Scully. So I was looking over Bill's resume for details on his career, which I know a little bit. Full disclosure, Bill and I went to college together. So I'll give you an arc with maybe a couple of punctuation points on them. So I believe when Bill was a student at Bennington College, he was a sculpture major. Is that right? Yeah, he was a sculpture major. And we didn't know each other terribly well, but we knew each other reasonably well. And during Bill's career as a student, he worked as a research intern at the American Numismatic Society. He was cataloging peace medals, which are basically proxies for treaties that were worn by native chiefs. It was that's the beginning of the divergence from being a sculpture major. That's what I'm trying to highlight there. After that, Bill did a bunch of different work. He ran a maintenance company of some kind for a little while. And it should also be said that this sort of checkered past is fairly typical for a Bennington College student, or at least we like to think it is. After that, Bill started developing a restaurant empire in southern Vermont, taking over a number of restaurants, running probably the only fine dining establishment within a number of counties, which is the Pangea restaurant down in North Bennington, Vermont. He did that for a while, and starting sometime around, 2009 or so, the Scullys started cleaning up old dams and retrofitting them to provide hydroelectric power into communities in southern Vermont, starting, I think, with a dam on the Williamsack River, right, the Vermont Tissue Project. And Bill not only can, but will tell you a whole lot more about this than I'm capable of, but suffice to say, as a brief introduction, that he was the first person to be permitted by the state of Vermont to build a new hydro project in 25 years, which is really quite remarkable. You'll see what I'm talking about when he gets into it. So basically, kind of the point I want to make about the arc of Bill's bio is he is a total omnivore of information and ability. And it's really, I'm just incredibly proud to have known this guy for all this time and to see all of the work that he has done, both in the state, at the college we both went to school, and now regionally and globally. So with that, I'm going to give you Mr. William F. Scully.
I promise at least an interesting little tale because I'm going to start off by talking about really who am I, which has become this kind of deep philosophical question for me. So January 26, 2008 is exactly when I got into hydro. I can tell you exactly where I was. I was driving along the Farmington River. It was about 2:45 in the afternoon, listening to an article on NPR about the rising price of oil. It was going to hit $4.58 a gallon, which was the highest that it had ever hit. So that's kind of the beginning, but the beginning, it's important to realize that I started doing what I'm doing really because of climate change, because I was worried at that point in time it was more termed global warming, but I had this epiphany. I have 4 or 5 dams right behind where I live and none of them are being used, and I'm thinking about that as literally every day there's energy pouring out of town. Why am I not driving an electric car right now that's powered by my backyard? So that's become this whole, and I'll circle back around to this, it's become this question of what is it that I'm doing, because and I mean that in a very real sense, there isn't a proper title for this. If I was in other parts of the world, in a third world country, I'd be a climate warrior. You know, the most accurate I think I might have found is conservator, because what I'm really doing is trying to manage public trusts, but to do so on a global scale. And as Nejem mentioned, as a developer, which is typically used in a derogatory sense, we redeveloped the first it was actually the second to be relicensed, but in 35 years. It had been 28 when I started. There had not been a redevelopment of any of the 1,200 dams that are sitting in Vermont. A few had come out, and I've actually supported some removal of dams, but nobody had been able to develop one. And I'm going to get into a little bit more about that. But I think so the whole thing is really, this has become this kind of exploration of who am I and why is there no title for this? Because there isn't a proper title for this. So let's talk about specifically renewable energy, because it's a little bit important to understand the basics. So some forms of nuclear, although it can be debated, will qualify as renewable energy. Geothermal is good, but geothermal really applies more to heating typically and not necessarily electrical energy production. There's biomass, but again with biomass you're giving off greenhouse gases. Wind, currently, and I'm going to frame all of this in the context of the state in which I live, which is important to realize too, that I'm not going to be speaking about Arizona because I don't live there. So right now there's a moratorium on all wind development in the state of Vermont. So then we get into, we're now down to solar and hydropower. Solar does a very specific thing, and I think a lot of people don't understand what solar does, because solar is very effective. Obviously you can't, at least with what we have now, power all our needs 24 hours a day because of night, and it would be quite the boon for Yankee Candle if we opted to go 100% solar, but we're not ready to do that right now. When we talk about Vermont, Vermont has 100 days of sun, and when you go to talk about how power is produced, you base Vermont, I think Burlington is 4.2 peak hours a day. So if you were to put in a 100 kilowatt power plant, you in a day, on a sunny day, would make 100 times 4.2 hours, so 420 kilowatt hours of actual unit production, which I want to explain that a little bit too. So when we talk about capacity, capacity is the amount of power that can be generated instantaneously. It's the actual, one way to look at it, although it makes more sense in hydro, is it's actually a function of horsepower. So, and I'll explain how this works, but kilowatt and horsepower are both units of power. When you think about kilowatt hour production, you're really talking about, it's a unit of measure like distance traveled. So you have the horsepower of your car and then a certain distance traveled. The distance traveled is actually the unit by which you measure production or distance or whatever that is, volume, gallons, things like that. So in Vermont, Vermont has taken a very, very aggressive, developed very aggressive programs with solar. And solar, so that we all understand, does one of the most important things in getting us off of fossil fuels. It takes care of peaking. So it just so happens that our peak energy use almost always happens in Vermont, and this is not reflective of Vermont. In Vermont, that's typically between, I believe, 10:45 and 2:30 in the afternoon is when the peak production happens. When you need, and utilities have to be able to provide the maximum amount of power needed at that time to everyone. They're actually required by law to do that. Actually, I think it's a factor beyond that 100 and something percent that that has to be available. So you get into instantaneous brokering. Sometimes it's day-ahead brokering, but the utilities are actually brokering in the instant to buy power, and most typically that would come from a fossil fuel power plant, coal, propane, natural gas, something like that, because you can't just fire up the nuclear plant and instantly have power. They don't work that way. So what solar does is, coincidentally, the sun's overhead in the window when you typically have peaking. So solar does an incredibly effective job at providing a certain amount of power at the time when peaking occurs, which means that you're no longer then brokering off of fossil fuel plants, which are really the only ones that can easily fire up and down like that. this was, I think about a month ago, maybe 6 weeks ago, that the Public Service Board put out a report on how the renewable energy programs have been doing, specifically group net metering in Vermont. What this is saying is that basically Vermont has just about accomplished the goal of solar. All the peaking now is starting to happen after the sun goes down, and solar can't be effective. So effectively, we have maxed out the potential of solar. It isn't that you can't add more, you can always add more, but you start to really see an extreme decline in the effect of solar in a grid like that, in any grid. So, next, hydropower. So, hydropower is also solar power, something people don't usually think about, where the sun really is the engine and the fuel is gravity. So the sun is causing water to evaporate. It's being moved around to higher elevations. It falls, forms in the clouds. It falls up high and it falls down. And with hydropower, you're actually capturing that water, gravity returning it to a lower point. That's all it is. The way it works is fairly simple. And I think Carol and I were looking at these images earlier. Essentially, there are two variables in how you figure out how much power, how much capacity you can generate, and it's easiest to think about it like this. You need two things. You need head, or elevation, because that's providing downward force, and you need flow. You need some kind of material to be flowing past the propeller. So with the different kinds of hydro that you can build, you always need to have the water drop a certain distance in order to provide pressure to spin a propeller, and the water travels through. There are a lot of different kinds of hydro, which I'm going to talk a little bit about that. But essentially, that's what matters. You're actually using, in some cases, you're building a dam to build up potential energy in a storage dam. In other cases, you're really just trying to build head. To give you an idea of how important the head is, every foot of head that you increase gives you approximately 10% more power. So head is an incredibly important variable in this whole thing. Different kinds of hydropower. It's really important to talk about that. My world is the world of what's called run-of-river, which is not this. Run-of-river, in the simplest terms, means that the outflow equals the inflow at all times. So our power plant ranges from, I think at the low end, like 15 kW up to 360 kW, and that is completely determined by whatever is given to us by the river. So, so I want to talk a little bit about the type of dams where there really is a cost, where you really need to weigh the cost of that dam, because there is a cost. Aside from things like fish passage and things you probably heard about, there's also something that happens with an impoundment like that, especially with an impoundment like this one. And I think there's an interesting argument I'm going to get into about Lake Mead and Lake Powell. But what happens with huge bodies of water like that is you lose a lot of water to evaporation. You lose a lot of water to ground penetration. But more to the point, you do two other things. You create areas that aren't easily habitable for the aquatic environment because it's rapidly fluctuating. You end up stranding fish, all kinds of other things. But you also end up with algae, things like that, that are actually going to give off greenhouse gases. So you can end up actually having a facility like this that's actually giving off greenhouse gases, which is why storage facilities don't qualify as renewable energy. Under the DOE, I think you have to be run-of-river. There may be a few storage facilities that qualify, but generally the Department of Energy would consider the environmental cost too high to consider a facility like this a renewable energy. And that's an important distinction. I like this picture simply because you can kind of see the cost. Look at there's a white line there. There's a white line where nothing's growing. The impoundment's going up and down. And so to a degree, you can, there are other costs, but I just like this one because there's just a line around the cost. And it's the fact that the impoundment's going up and down. And in this, it does still provide a lot of good. A facility like this, even though it's not renewable energy, can perform the function of a fossil fuel powered plant. There will be a bunch of turbines in here, and what happens is overnight the impoundment raises, and then when peak flow is needed, they draw it down. They just fire up more turbines and bring them all online, bring the power up, and they're actually able to provide nearly instantaneous power. So, pardon me. So we need to look at the fact that what I'm working with is run-of-river. There's another distinction too in the simple mechanics of this is when I talked about capacity being a function of power, but then you're generating a certain amount of volume of energy in kilowatt hours. A hydro plant, people get confused in saying we need to put in this much capacity, we need this many megawatts or gigawatts of power, which isn't true because depending on the technology, you get a different result. Our Pownell plant that will be live in about 2 months will generate about 6 times as much production as a solar plant. Keeping in mind too that we're talking about Vermont. So the same solar panel in Arizona gets you twice as much power as it does in Vermont. So in Vermont, we can generate easily, I think we're at 6 or 6.2 times as much production off a 500 kilowatt plant as a solar plant would get you. And getting back to how things are different, there's a clear cost you can see in this dam. And where things changed is when we did Vermont tissue, because we really brought the stakeholders to the table very early. Carol was actually really helpful with that. And we ended up with building what we think is the first and only hydro plant in the world that actually improved the water quality. And I think you'd find that there are quite a few people that work for the state and environmental groups within the state of Vermont that agree with that statement. They've actually made that statement to me, that they're not sure if we can repeat it, but we built a plant that actually made the water quality better before accounting for it being a renewable energy and staving off climate change. So, and the reason we did that is that we actually saw the concerns of the stakeholders who are the environmentalists as actually design issues, design problems to solve. We just tried to build a better mousetrap, and we did. We built, and I'll show you in a bit, an entirely unconventional mousetrap that at the end of 20 years had about $1,000 difference in what the returns were. It was just a matter of thinking through the problem and looking at them as opportunities. So, it's always good to talk about why are we doing all this? What's the big picture? Well, the big picture for me is climate change. And boy, we are in some interesting times. And I keep having to remind myself of some of these things, but and some of the facts too. So Arctic ice coverage has decreased, and obviously everybody talks about sea level rising. What does that mean? It means New York City was going to be renamed as New Venice City because it will be underwater virtually. I think after the Paris Accord, everyone's pretty much agreed that's going to be a result. Vanuatu, Samoa, island nations like that are only a couple meters above sea level are gone. So they will go away. That's the result of sea level rises. And I don't think there are many people who are climatologists who are going to tell you they don't think that's going to happen. I think that's pretty much been decided. Here's an interesting one that I was actually really upset that I didn't know earlier. I was actually terribly upset that this hadn't been made clear to me. So when we talk about the polar caps melting, it's not that the sea levels rise. That's a result. That's not the problem. The problem is the feedback loop. You're taking a reflective surface that prevents global warming and turning it into an absorptive surfaces that retains heat. That's a big problem. And you actually hit a point where you can no longer turn back from that, which is one of the things why people are talking about 2017 is a pivotal year. And I don't know if that's right, but I think most of the information I read is that 2017 we really need to make some decisions. And if we don't, all of these feedback loops will lead us to a result that we can't stop, at least not with any technology that we know about now. The acidity of the ocean is changing. So here, more than 1 million species face extinction. 25% of the mammalian population right now is facing extinction due to climate change. Another feedback loop. So dissolved oxygen, which anybody who works with rivers, dissolved oxygen is pretty important. Well, dissolved oxygen in the ocean disappearing means that you end up with microorganisms that tend to give off nitrous oxide, a greenhouse gas. Again, a feedback loop. The more global warming and climate change that you have, the more you're actually creating things that increase that. Here's another one. So Desmond Tutu was talking about the 2 degrees that the Paris Accord, and I think they were talking about 1.5 or 2 degrees, that the Paris Accord discussed as being the average that we're set. That's tracked. We are going to increase by that much. And I think people were saying, well, we can live with that. And Desmond Tutu said, well, you can, but I can't. Your 2 degrees is 4 for me. We can't farm at that temperature. Africa will become entirely uninhabitable at that point in time. And world food crisis right now, inevitable. And we've known about this for 20 years. that the Himalayan glaciers are melting. That's what's providing water for not just fresh water for drinking, but I believe something like 50 to 60% of China is fed on rice and other things grown with that water. That's, I mean, if people are complaining about immigration problems now, when there's really no food, it's a problem that nobody's even really wrapped their head around yet. So here's where I am, and I'm looking at it, and I like science, and I'm kind of thinking, with everything that's going on right now, we are the second largest oil producer in the world and the largest consumer of oil. We are the oil industry, which is why we are the only country, I'm sure you all know this, but it's worth saying, we are the only country in the world that doesn't agree that climate change is happening. I don't have the words to describe that. I can't wrap my head around that, but that's the facts. We're in the business of oil, which is why we're not doing that. So, what I did is I set out, again, December 26, 2008, driving along the Farmington River, and I had this epiphany. And it's really kind of a cool thing when you have an epiphany that changes your life. And I decided I wanted to find out about hydro. So by the 27th, I had done enough research that I kind of understood why hydro hadn't happened. I like number statistics. 3% of the population had successfully staved off hydro production for 28 years by that point in time. 97% of the population of the state of Vermont actually wanted more hydro development, and none of it was happening. Reason for that? Pendulum had swung the other way. In the 80s, there was a whole lot of really unregulated hydro development. A lot of things happened. I think a lot out west, but also in Vermont, in Massachusetts, all around. Actually, there was a lot in New England. And because so much development happened then, the Federal Energy Regulatory Commission and the states, more specifically the states, couldn't actually track it. Most of the water quality certificates started coming in after the license, after the deadlines. And so the states' rights didn't get properly vested into a lot of these. Their opinion really didn't make it on the record. And everybody was rushed. So that's why we had no new hydro development. In the meantime, all the hydro developers had gotten so angry that when I went to the House of Representatives one time, and people were just swearing at each other and getting up and walking out of the room. And this is how the conversation was being conducted at the highest level of government in the state of Vermont. No one would actually sit down and come to the table. So it's really kind of interesting to think back on what shifted, and there's a couple really pivotal moments. So this involved changing a lot of the legislation in the state of Vermont. I don't know how many rules and laws and bills that I've actually helped draft, but we actually had to change policies and change the minds of people, but we had to do that by actually involving them, which is the step that hadn't happened from the people trying to redevelop hydro. They hadn't really gone out and sought out the opinions of people early on and tried to incorporate those concerns as design elements. What we had though at this site, kind of a cool site, the oldest paper mill in the state of Vermont. The state constitution drafts were made there, which the state constitution of Vermont is the first document in human history to outlaw slavery and address suffrage. So it's kind of a cool legacy of this old mill. And I don't know, I try to live up to that, but it's a really strange site. So we have 3 established waterways. We had, when you look at this, I don't know if you can tell, but on the far left is our tail race. And the tail race always sits a little bit below the river. We have a main channel with the water flowing over, but in pink over here, we also have this emergency spillway, which is a dam that sat about 5.5 inches higher than our primary spillway. Also an ephemeral river, so that during about 17% of the time, there wasn't enough water in the river to actually wet that area, which is actually the natural bedrock falls that existed when people got there and why they built a mill there, because there was actually natural water power. There was a naturally occurring dam. And it had since dried up, and it's a great little passage. So some of the things we did, I talked about, we built a better mousetrap. We had 2 turbines. Rather than discharging both into the tail race, we actually discharged one into the tail race and one into our main channel, which gave us some interesting opportunities, because then we could go to the state and say, what is optimal? What are the optimal flows? Because this is all computer controlled. If you want 108 CFS here during spawning season, but you want to back that down to 60 off season, we can do that. And then we put the rest over in the tail race. So the state actually designed our flow regime to maximize the flows for the aquatic habitat. And again, terribly unconventional design. How did we make, and so 3.5 feet difference in head. So one of our turbines is making about 35% less power. How do we make that back up? Well, first off, we didn't have to deal with addressing putting a certain amount of water. It's called 7Q10. It's the lowest flow for 7 days in a 10-year period, and that would be the minimum amount of water, which in this case was about 22 cubic feet per second, or about 22 kilowatt at that head. We didn't have to actually put that in because we were actually already watering that reach with water from the turbine. Number two, we put in this screwy little wall. We put a weir in the training wall. What that allowed us to do is to provide, to address stagnation and dissolved oxygen in the tail race and keep water moving through that reach so it didn't stagnate by providing water that we had already made power on. So we're using water that we've already generated power with to provide for our low flow water quality in the tail race reach. We took in that section number 3 and we cut another weir in that dam. And we said, okay, well we can take this dam. We matched the 2 dam heights. We just put these simple little flashboards which fail during high water, but we matched our dam heights. So now we had the same amount of water going over both dams all the time. And then we said, okay, well, let's cut a weir in the emergency spillway dam 2. Let's just set that at whatever it was, 12 or 13 cubic feet per second. Actually, it's 15, I think. But anyway, we set that with the state. It's pretty straight-sided, so we figured out what we needed to provide to keep the aquatic habitat there good year-round. So now we've taken an ephemeral reach and turned it into a permanent reach, which also acts as fish passage now because the dam that we cut the hole in is between 2 and 6 feet high. It's actually just a cap on a natural bedrock falls that runs about 200 feet. We distribute flows based upon the habitat needs. So before, the flows were split roughly evenly due to the failed wall, but now we put the water in the shallow, fast-moving reach during a certain time, and the deeper reaches during another time. Aside from that, you wouldn't believe the amount of litter. So we have these trash racks that catch sticks and leaves. Boy, do they catch leaves. But they also catch all the litter. So we're actually a source of pulling all that stuff out. There's a lot of other things. We took the entire island in the middle there and turned it into a park. We cleaned up 126 tires out of the river, refrigerators, stoves, all these other things. It actually took us several years, and a lot of community members came out and helped. But we ended up cleaning up this entire area, putting in portage, doing all that stuff. And for us, the park was a real win because it was a dump. I mean, it really was a dumping ground. It's where everybody went and dumped their trash when they couldn't afford to go to the dump. So in cleaning it up, we realized that we could populate it with the people that we wanted to have there, and then suddenly it became self-policing. Suddenly all the people that wanted to go there and fish and kayak and all these things started policing it for us, preventing the litter, preventing people from dumping garbage, all that kind of stuff. The partying, all that stuff. And as a byproduct of this, dams catch different types of sediments, coarse and fine. Some of them carry actually an electrical charge, and they'll actually pull metals out of the water. Others don't, but they actually will grab different kinds of material like dioxin and PCB. They actually filter them really well. So in doing this, we ended up, I couldn't tell you the volume, but we pulled out a whole bunch of dioxin, PCB, and lead from the river. I mean, when we pulled the material out, it was black, and it took me about a month to remember the smell, but it smelled like a photo booth or a photo developing shop, if you've ever been into one of those. And I think it was the lead or something. But anyway, so we got all this cleaned up, and we ended up with this project that actually improved the water quality and is a renewable energy project. In doing it and in cleaning up the PCBs, the dioxins, the lead, all that stuff, nobody had really done that before. And so we came out with this odd tool set of knowing how to clean up contaminated materials from the river as a byproduct of redevelopment, which brings me to the next project. So, one-of-a-kind project, because there is no other site in the country where you have PCBs from a former plant in Massachusetts that have come into Vermont, that have deposited in Vermont, ending in 72, I think the Clean Water Act prevented anything else from going in right around then, but they're all still there. And they're all still, the amounts are slowly decreasing because, and it's not magic, they're actually just slowly leaching back out into the river and heading on into New York State, into the Hudson, which New York is psyched about, I'm sure. So what we realized then is we're actually in a, it's a little hard to tell, but this whole thing is cut into bedrock. So we then stepped in, and the plant had shut down in 1988 was the last time it generated power, and I think they boarded it up in 89 because nobody could figure out how to get the PCBs out of the river. EPA obviously didn't want them just released downstream, and there was no protocol for managing this. And people had tried, I don't know how many developers had tried this, but we said, okay, well, 13 miles up that way, we just did this. So we could come in here, we could run some HEC-RES modeling, we could figure out the hydraulics, we could figure out, using core sampling, what the depth of the bedrock is and what we need to remove. So we went in and we isolate the area. For the most part, we dewater the area, removing the dry, but we keep it isolated from the river, pull everything out, dewater it, send it to a solid waste landfill. Again, doing this as a byproduct. So for the first time since 1988 that we know of, we're actually able to come in and self-fund starting to clean up some of these rivers. And this is a class 3 water. You can't swim in it, you can't eat the fish. Like it's really not pleasant. So all the silt, actually all the contaminated material is now out. And we should be online with this plant. I believe in May we should be commissioning. We're on schedule to commission in May. So this is all kind of good stuff. And with this site, we actually stepped in and wanted to amend the capacity. It's called a non-material amendment. We're not changing any of the flow regime. We're not changing where the water comes in, the water goes out. We're not changing anything other than the fact that we're not using a turbine that was made in 1908, actually in Orange, Massachusetts. We're going to put in a new state-of-the-art turbine, computer-controlled induction generator. And because of that, we can actually generate 500 kilowatt, not 400 kilowatts. So we went to the Federal Energy Regulatory Commission and we said, look, we want to increase our capacity by 100 kilowatt, but it's a non-material exemption because we're not changing anything other than what the sticker says and the amount of power going out. And here's where I started to realize some kind of confusion in what I was doing. Because we caught a lot of resistance with this. And the resistance was based on, and I'm quoting, that dams are the most harmful thing to rivers. Which kind of caught me off guard. I didn't see that one coming. I ended up actually really liking this guy that made the comment because I pushed back a little bit and I filed my testimony and I said that's entirely true as long as you completely ignore the fact that climate change is happening. And it started to open this thing up that they're not actually viewing it as if climate change is happening, because if climate change is happening, that's clearly the most harmful thing to this river, aside from the PCBs. And so it kind of opened up for me a way of looking at it that I hadn't thought about. I've supported dam removal in North Bennington. I wrote an article I'm sure you can find called The Developer's View on Dam Removal. I'm not opposed to dam removal, but when you have good development, why am I hitting opposition at all? Why am I not, when I'm the guy cleaning up the river and I'm not asking for anything, that's fine, but why am I hitting resistance on this? And it became interesting. So what I did is I got involved in the next project, which is Swanton, which you couldn't find yourself a more contentious project. And that's actually why I'm doing it. I'm doing it to make a point. And I don't mean that sarcastically, I don't mean that in any way other than I actually strongly disagree with the position of the environmental groups in the state of Vermont right now. And I think I'm right, because I'm using math, and I love math. I think that there's a problem in how people are looking at the total project economics. There's an ideology, there's one fellow who I have to wonder about with Lake Champlain International, who all he wants is a dam out in his lifetime. That's all he cares about. He won't come to a meeting, he won't talk about it. This is what he wants. That's not how you handle a public trust. That's the opposite of how you handle public trust. The public trust should be handled as a public trust, as the public's trust, not as one person's ideology. So when we stepped in, we looked at it, and again, we said, okay, let's look at this. Problem number one. This is the last dam before Lake Champlain on the Missisquoi River. And they want to try, I don't think that Lake Sturgeon could get there, but they'd like to have the possibility for Lake Sturgeon to get up for the next couple of miles, and then there's a 45-foot natural bedrock falls. They couldn't go any further. So we're talking about between 2 and 4 miles of river. And they said you can't do this because there's 2 endangered species there, because you have to be able to provide for lake sturgeon passage, and although 2 people really have tried, nobody's done it successfully. And again, me being me, I'm like, well, that sounds like a problem we should solve, right? Let's see if we can actually try to design successful sturgeon passage. And as it happens, the design problem with this site is there's too much water. There's just too much water. This dam starts at 12 feet and goes to 7 feet, and the flow at the 85% exceeds, well, the median flow, let me give you that one. The median flow is 2,000 cubic feet per second. You simply can't put it all in one place. You would have no head left. I mean, the water would go straight through this thing and you wouldn't be able to generate any power. So the design problem is you actually can't, unless you put turbines all across the dam, which would cost a fortune, you can't actually use all this water. Cool. And you want the dam out. Okay, what if we took out part of the dam? What if we took out part of the dam and actually tried to make a bypass, a deep water, relatively slow moving bypass with lots of riprap? We need to keep the water moving slow to try to move these fish around it. We proposed that and the bar moved. Now the bar is we don't want to have an impoundment at all. So that's when I really started scratching my head again and wondering, am I playing on a level playing field here? Because hydro is, make no mistake, it's the hardest thing I've done. Run many companies at one time, a couple hundred employees. This is really hard, and it's hard for a really good reason. It needs to be hard because you're dealing with a public trust. It should take 5 years. It needs to take that long. One of the reasons why comes out of this 1972 Clean Water Act. Specifically, most specifically to what I do, is something called the Anti-Degradation Act. The Anti-Degradation Act means I can't come in and make the water worse. And going back to thinking about Vermont tissue, and I said I would touch on this, one of the things we did that really changed things is all of this fighting was happening in the state. The legislature, everybody was swearing at each other, and we posed the question, well, I actually said, I don't want to talk about what you don't want. Let's have a conversation about what you want. The technology's here, we can build it. Rather than talk about let's not make the river worse, what if we try to make it better? And in taking that and trying to apply the Anti-Degradation Act in a different way, it should apply to all these projects, and it does apply to all these projects as long as they're hydro projects. The second you're not a hydro project, the bar changes, and that's where I really tend to find a bit of a problem. So the plan for this dam, and I don't say the plan hypothetically, the actual plan is to remove the dam, release the sediments downstream, expect massive die-offs, probably lose 2 endangered species, and that's the plan. And that is allowable in the state of Vermont. I think it's illegal, but it happens all the time. And again, I'm not opposed to dam removal, and I don't know if we'll develop this site. I actually want to get to the truth. What is actually the right decision here? Is it okay to decide? I mean, talk about privilege. People talk a lot about white privilege these days. You want to talk about privilege? The fact we can have a conversation about whether or not there's fish passage, and that result is a feed-in to whether or not Africa can feed itself, is an interesting thing, and we should take it that seriously. I don't think it needs to be taken as lightly as it's taken sometimes. So where I'm pushing is, all I'm trying to do with these projects, especially with Swanton, is even if I don't develop that site, I want to make sure that the decision that is made has the correct values, that that the full economics are looked at. And it really is, and I talked about economics a little bit ago, it's a dispassionate process. It's an economic problem. And I don't mean just financial, I mean social economics, environmental economics. It's actually an economic problem. So I started looking at this and I started having these kind of eye-opening things. This gets into who am I, because I'm trying to figure all this out. And one of the interesting things I learned is that the word environmentalist, as it's used in this country, does not actually mean you're trying to save the environment. For one reason. It's mainly because of looking at things on a small scale, whereas I'm trying to look at them on a big scale. I'm not trying to look at whether or not the fish, the aquatic habitat will be improved for the next 20 years, because it actually might be. I'm not arguing that. But what about the next 20? Because the next 20 may not be there. And does any of this even matter if we can't get beyond the first 20? So, again, I'm not trying to, a lot of the people that I'm talking about, I really respect. when I talk about the environmentalists. I actually do, and my projects are good because of them, and I realize that. But what I'm talking about is the fact that somewhere in here, there's this gap where there are people doing things that are environmentally oriented. There's studies, there's climatologists, there's all these things, and it's hugely valuable. There's people helping me drive my projects to be better projects all the time. But somewhere in there, there is actually the need to actually implement this at a much more rapid rate, or none of it's going to matter. And there's no name for that. I'm a developer. Great. I'm the same as all the people trying to put in the Dakota pipeline. My underwear says the same thing on it. We all have the same title. I don't think that's an appropriate title. When's the last time you heard Elon Musk described as an environmentalist? I don't know much about him personally, but I can tell you with all he's done with electric cars, with solar, with everything like that, he's made huge advances in staving off climate change. But he's a billionaire, he's a this, he's a that. He's not an environmentalist. He's a business owner. And I wonder why we don't have a word to describe somebody who's actually trying to stave off climate change by implementing renewable energy systems. That isn't the same as somebody who's trying to put in a big oil pipeline. So again, this is reflective on me of trying to figure out what's that next step beyond trying to look at the local environment and try to look at things globally. So I think that one of the things is I tend to look at the entire planet as the trust. So when we talk about public trust, I think that I want to make sure that I'm talking about, yes, the river is a public trust, but the entire planet collectively is a public trust. And if you can't look at the entire system and the impact of a small part of that trust to the bigger part of the trust, I don't think that the entire story is being told. So back to, again, I supported dam removal, and dam removal is something that is happening at a much more rapid rate in the state of Vermont. Infinitely faster dams are coming out than going in. I don't know much about there being the same criteria under the 401 Clean Water Act being applied to that, at least as far as what I know that it isn't, as far as whether you're going to kill off species or whether you're not, whether you're going to test for contaminants or anything like that. But the thing is, I don't think that there's a level playing field, and that's what bothers me. And managing public trust should actually be a really dispassionate process. It's actually just math. The numbers don't have an opinion. I'm actually just trying to find out the truth. What is the best net result for a specific waterway, whether it's hydro or not hydro? So basically, I'm looking for a fair and equal interpretation. Now, here's an interesting one that is outside of my area. Has anybody here heard of the Fill Mead First? I'm assuming somebody's heard of that. It's talking about two dams. The one that holds back Lake Mead, which is the Hoover, and Glen Canyon, which creates Lake Powell. And there's an argument that has been made that one of those dams should be gotten rid of. And it's been going on for 40 years or something like that. And one of the things I found annoying about it is that there's actually like numbers at the bottom of this thing. When people talk about increased evaporation, that's totally true, but there is a net number, and you can achieve that net number. What's the net number? Give me the numbers, give me the facts. And I don't know if anybody's actually run all that modeling, which isn't actually terribly hard. So the water per gallon may actually slightly increase in evaporation with turbulence, because if you're going to move it faster and over a more porous surface, you're going to end up increasing to a degree how fast it evaporates, but it's going to stay in the region less. It's just math. But I think after a while, they've actually come around to one of my favorite arguments, which is, what about if we bypass it? What if we bypass the Glen Canyon Dam? Don't get rid of it, because we don't know what's going to happen in 20 years, and who needs a $50 billion infrastructure project when it's already built. So I actually find what they're doing to be an interesting conversation. It's just that nobody's gotten to the whole truth, at least not that I've read. I haven't seen anybody actually question numbers on that. So again, and I don't want to forget about the fact that a lot of the people I'm talking about that are with the environmental groups are friends of mine and people I respect. And in some cases, a lot smarter than me about this. So I don't mean to sound like I don't have a lot of respect for them. I do. I'm just trying to figure out how as a state and as a country, we're applying different standards with a result that could be a catastrophic result. So, economics and values. Again, I get back to trying to solve the environmental problems thinking globally. Yes, we have to think locally, but we also have to add in the global perspective. How do we do that? So I think in large part, in my opinion, it's actually more people should be involved with the environmental groups. And if your opinion is like my opinion, that these things are important, that thinking globally is important, then it's important to say that. Because right now, at least where I live, there basically is a climate denier position in all of them, that all dams are bad. That's not a true statement. That's actually just propaganda. It's not a true statement. There are actually really bad dams. I completely would concede that point without any argument at all. But there are also a lot of good ones. And if you go look at the websites, you'll find a universality in the fact that all dams are bad and need to come out. So, just gonna go to a nice pretty picture. So here's where I am in trying to figure all this out. Because when you think about it, all the big oil needs to do to celebrate a win right now is buy the champagne. Because most of the environmentalists, climatologists, the people who are developing hydro, developing solar, really there's so much infighting that, you know, big oil doesn't have to do anything at this point. We're actually combating ourselves to a degree that we're halting our own progress. It doesn't mean that you throw out all the rules and quit having healthy debates, but the fact we're debating things that shouldn't be debated or that don't warrant that debate or that we apply an uneven playing field, for me is a pretty significant problem. And it's a big waste of time. And we're not winning at all. So it brings me to the question of, can an environmentalist, and this is just a question, can an environmentalist take globally a climate denier position in the definition of the word, in the most fundamental sense? Because that's actually happening. That's actually the position in many cases. And how do we get to this position? You look at the presidential debates, climate change wasn't debated. I don't know how that happens. I don't know how you get to right now having a position of national defense when I'm going to read this, in 2012, U.S. generals declared climate change the greatest threat against the United States. The Pentagon recently stated that the DoD recognizes the reality of climate change and the significant risk it poses to interests globally. The National Security Strategy issued in February 2015 is clear that climate change is an urgent and growing threat to our national security, contributing to increased natural disasters, refugee flows, and conflicts over basic resources such as food and water. These impacts are already occurring, and the scope, scale, and intensity of these impacts are projected to increase over time. And really, our national defense strategy right now is bury your head in the sand. It's not happening. It is happening, and at the highest level of government, at least in the military, people recognize it. So what are we actually doing? Well, at least in Vermont, great representation, our legislators fought hard to get what is most commonly dubbed as 90 by 50, to hit 90% renewable energy by 2050. And they fought hard for this. And it's inadequate. It's inadequate and we can do better. How many countries have hit 100%, even if they can't maintain it, or sustaining 80, 85%? And this isn't a matter of wealth. Yes, Germany, of course Germany's in there. Germany, Denmark, Spain, Iceland, Paraguay, Albania, Bhutan. I mean, the list goes on and on. There's dozens more that have done this already. And we're looking how many years in the future when we hit 90%? I mean, it's really interesting what our value system is, that we don't place the value on this higher. To give you a really, going to wrap up in a second, but to give you a really fine point on it. We built a net metering group at the Pownell plant. Biggest net metering offer in the state as far as production. The largest financial incentives ever offered in the state, because we are a source meter. Our meter runs backwards. We're generating all these kilowatt hour credits. We then need to apply them to other people's bills. In doing that, they then pay 95% of that to us. They get a 5% savings on their bill. And we're not talking small dollar amounts here. We're talking huge dollar amounts. We called every company in the state of Vermont within the grid, which is 85% of the state, that was large, colleges, universities, you name it, big business. And after 6 months, we found 2 that were interested. To say it just as clearly as I can, In Vermont, which I would consider a progressive state, you literally cannot pay people to do the right thing. Just think about that for a second. I can't give away money to get people to support renewable energy. It's staggering to me. And that's the state of the world today. That's the value system we've set up. It's not their fault. That's actually the value system that we have created as a culture, and I think it's seriously flawed. So anyway, the story here isn't how I did this, because I'm just, as Nejem described, somebody that likes to do stuff. Lots of stuff, and the more math, the better. And if you knew me, you actually couldn't imagine how ridiculous I find it that I will own 22% of the net metering in the state of Vermont. I don't know how I even fell into this field other than trying to affect change. So I try to figure out what my role is. And I know I owe a lot of my successes to other people, and one of the most important points was sitting down, was actually with a fellow named Brian Fitzgerald, and realizing that I was right and righteous in my mission, but also realizing that he was right too. That was the game changer for Vermont Tissue, was realizing that there is more than one right. So what's the sum of that? Is my job title somebody who's right? More right? I don't know. But it's important to think about actually being right, and the fact that there can be plurality in being right. And I think that that's a point that's missed on us, that there can be more than one right, and those rights can actually figure out how to work together. So what I'm trying to do really is to tell the complete truth of things. And I think that's actually what's missing, is the complete truth. We're not going after all those rights or wrongs or whatever it is. We're actually not checking all the boxes to get these things done. And it's about the total economics, not the sound bites. They're complex issues and deserve our attention. So I know one thing, that we've known about climate change for nearly my entire life. And nothing else matters as much as this. I actually know that. All the things we want to talk about in politics and government, what difference does it make if we're all dead in 50 years? Is that our legacy? Do you know that when you talk to physicists and scientists who are looking for, is there life on other planets? Does anybody know why they don't think we're ever going to find it? Because it doesn't last long enough. Because we're actually, once we get to being intelligent, we aren't actually intelligent enough to stay alive. That we're all just blips. So who am I? I don't know. What I do know is that if we're going to save the planet, we might actually want to start by creating a job position and posting the position. And I think it's time to decide what we want, really. And the fact that I can't describe that with a word that everybody would know, yeah, that's what he does, is kind of a problem, culturally, for us, at least in this country. So thank you very much for my crazy rants.
Woo!